Uh, please take a seat. We're about to start our next talk. Next talk is by Víctor Verdugo. He's the assistant professor at Universidad Católica in Chile. If you were here for tutorials, I promised he would talk about this demand problem. He will give the most recent picture on this problem. So thank you, Víctor.
Thank you. Thanks a lot. And thanks a lot for the invitation. Yeah, so as Andres just thought, I will tell you about some recent results that we did with José Soto, which is a professor at UChile, and also with Javier Marinkovic. Javier, actually part of the work is the master thesis of Javier. It's excellent student. And he moved it to Maryland for a PhD. So I hope we will see him here. So, all right. So, well, let me start with a brief recap of the combinatorial allocation problem. So this is essentially what Andres showed yesterday. Let me briefly show it again. So I will have n agents, okay, and a set of items. Yeah, so that we call I with a set of items. And each agent will have a valuation function, Wj. And Wj will be defined over subsets of items. Okay? And it will take positive values. And the goal is to find the maximum welfare allocation of item bundles. So meaning I will pick subset of items, okay, and I will assign this subset of items to the agents in order to maximize the total weight. But I have one constraint, yeah, which is that they should be all disjoint. What does it mean? It means that I'm allocating only, so every item is allocated only once, right? So I cannot allocate an item more than once. Therefore, let me give you an example. So let's say that here I have 3 possible bundles, yeah, and 3 agents. And for the first agent, maybe the top selection is, I don't know, the bundle in blue, let's say, with a weight of 6. And then for agent 2 is the one in red with a weight of 8. And for agent 3, the one in green with a weight of 10. Yeah. So let's say that these are their most preferred bundles. Okay, if they have to choose, that would be the choice. Okay, but the problem here is that this is unfeasible, right? Because I'm allocating items more than once, right? So they intersect. Okay? So then this is not a feasible allocation. Okay, but on the other hand, this is a feasible allocation, right? Because here I have again these 3 bundles, right? So maybe the values are lower, right? And maybe actually every agent will be more than before, but now this is a feasible allocation. They do not intersect, right? I'm allocating every item at most once. Right? And possibly some items are not applicable. Like in principle, that's possible. And of course, as you can already see, the problem will be very hard, right? So we can encode hypergraph matchings by solving this problem. And now, as Andres said, for the rest of the talk, I will focus on the setting in which agents demand bundles of size at most k. So this is where they put all the value. Yeah? So essentially, they only care about selecting k items and not more. So how do we model this setting? Well, I will model this as an optimization problem over hypergraphs. So the nodes in my hypergraph are given by the set of items. Then each agent has a weight function over the set of hyper edges. So imagine that every hyper edge, now it's a possible bundle. Right? And they have size at most k. And again, the goal is to find a maximum weight allocation of disjoint hyper edges, right? So therefore, I'm looking for a matching in my hypergraph. So the problem, well, it's hard, right? But let me show you an integer program that will solve this problem. We will use it later. So in this integer program, I will have for every agent and for every hyper edge, right? For every E, I will have one variable. It's a binary variable, right? XJE. And the variable will indicate whether agent J gets the bundle E, right? The hyper edge E. And the first set of constraints, I'm just saying that every item cannot be allocated more than once, right? Because in the left-hand side, I'm taking the summation over every agent and over every hyperedge incident to an item, right? Every bundle incident to an item. And then in the second set of constraints, I'm saying that every agent cannot receive more than one bundle, right? Maybe no, but not more than one. And then in my objective, I'm maximizing the total weight of the allocation, right? So I'm summing over the agents over the bundles of the weight. Good. So far, so good. Okay, perfect. Now, okay. Okay, now the online setting, right? The online setting. Okay, so now the agents arrive sequentially, one by one. And each agent has a valuation function, again, Wj, right? But let me assume here, so Andres yesterday showed an example that if you do not assume anything, right, about the environment, essentially, if the environment is fully adversarial, then you will not do anything good, right? It's very, very good, right? So then in my setting for now, let me assume that every agent has a valuation function that is drawn according to some distribution. Okay, so it's a random valuation. And it is even the same for everyone. So then I'm in the IAD setting for now. And then upon arrival, have to allocate or not a bundle to the agent. Right? So again, a feasible solution should look like this, right? They cannot intersect. Right? Every item is allocated at most once. And what's the benchmark? Well, given the profile of weights, right, for every agent. So you solve the IP, right? That will give me the optimal welfare allocation, right? And then I compute the expectation of that. And this is my benchmark. All right. Good. Okay. Now let me show you one algorithm for this setting. Yeah. So again, let me recall. So I'm in the IAD setting. Okay. IAD. Okay. So at time t, I will do the following. I will sample n independent weight functions according to the. Yeah. So like one per agent. Essentially. Okay. Then I will pick a uniform random value. It's a uniform label, essentially. A uniform algorithm. Yeah, between 1 and n. Okay, now I will solve the optimization problem. I will solve the integer problem. Let me show you first this low algorithm, right? Because of course I'm relying on solving an NP-hard problem, but just for simplicity, let me cast it using the IP. Okay. So you solve the IP and X is the optimal solution. Okay. And then you look at the solution, right? Given according to the label, right? So again, so for every agent, right, what you have is a vector, right, with a 1 and or a 0 on every entry, right, saying whether you pick that bundle or not. So you will have at most 1 in that vector, right? But it could be 0 completely, and this is saying that you allocate no bundle for the agent. Okay, and if this is the case, well, I don't allocate anything, right? So the agent will have no allocation. But otherwise, right? I know that in that vector there exists a unique 1, right? And this is the bundle that I will give to the agent. Okay. Plus one more filter, okay, which is keeping feasibility. Right. This is the one more filter that I have to add because maybe the IP is saying, well, you should allocate the bundle to the agent, but then when I want to include it in my solution, maybe it's intersecting a previous bundle, right? So as long as it remains as matching, I can allocate it. Good. All right. So I will show it very sketch, okay? So I'm not putting all the details here, but just to give you some idea. Okay? So with this algorithm in the IID setting, you can get a 1 minus e to the minus k over k approximation. Yeah, which is slightly better than 1 over k, right? Slightly better than 1 over k. Okay, so then let me elaborate about the contribution of, let me elaborate about the total weight of the algorithm, right? So I will split it according to the time steps, right? I will split it from t equals up to 1, right? And then essentially, so the contribution of the weight, right? Of the hyper edge allocated at time t. Also here, let me assume that again, if you do not allocate anything to an agent, then the contribution is just 0, right? That's okay. So they would be essentially like 1 over n the expected out. Okay? Be essentially. But here comes the most interesting part where you have to pass the filter, right? This is the condition to entering in the solution, right? If you want to actually allocate the bundle to the agent, then it should be that it doesn't intersect any previously allocated bundle, right? So I want to compute, in other words, for everything, I want to compute the probability that the selection of time t is not blocked by any previous selection. Okay? And by blocked, I really mean intersected, okay? Like in the hypergraph notion, right? Okay, but imagine that you fix, fix the selection of time t, right? So that this is a bundle, it's a hyperedge. And then look at any previous step. Okay, look at any previous step. So what is the probability that in a previous step, a bundle assigned by the algorithm could block this fixed hyperedge? So the size of the hyperedge is at most k, right? So then I could be blocked by at most k possible choice, right? Over the n. So then for every I before, with probability 1 minus k over n, I do not block the selection of time t, right? And then from here, we are essentially done now, because now what you get, right, multiplying the benchmark, the 1 over n, the summation from 1 up to n, of 1 minus k over n to the t minus 1, right? And this thing, well, it's just equal to this, right? 1 minus 1 over minus k over n to the n divided k over n. So then the 1 over n with this other n, they cancel out, and then you recover, well, I'm giving 1 third. So you recover 1 minus k over n to the n, but this is at least all the time 1 minus e to the minus k. So then you get adding to the 1 minus e to the minus k over k. Yeah. It's a simple algorithm, and it already gives you something slightly better than 1 over k. Right? Excellent. Okay, let me comment a few things about the algorithm. Okay. So first of all, in the description, I used the IP, right? But of course, solving the IP is too much, right? So I don't want to solve the IP. Okay, the first observation is that I can use DLP, so I can use the linear relaxation. Okay, and then you have to change the algorithm a bit, okay? A bit, but in a simple way. So let me describe it. So what you essentially do is that the last 2 steps of the algorithm, you replace them in the following way. Instead of just looking at the integer allocation given by the IP, you will do the following. For every agent, you will have now a random allocation. Okay? So it's the EJ. EJ will take the value of a hyperedge with probability xj of e. So it's essentially the probability given by DLP. Right? And it will have no allocation with the rest of the probability. So if you look at the second constraint, I'm saying that for every agent, right? For every agent, the summation over the hyperedges is at most 1, right? So it's not exactly a probability distribution, but what I'm just saying is sample according to exactly the same values, okay? But with the rest of the probability, then you allocate nothing, right? So this is exactly the same as having one extra variable, right? So you get a per agent, one extra variable saying that you allocate nothing, and then in the LP, you put equality, right? It's the same. So then essentially here I'm doing just independent sampling, right? With replacement, okay? With replacement. Just independent sampling, nothing more. Okay, and then in the last step, well, if your allocation is empty, right, then don't do anything. And otherwise, well, you check, right? So you check the filter again. So you say, I want to allocate this edge for the agent, but first let me check that what I have is feasible, right? So it should be a matching. And if you have a matching, then you allocate, right? So you pass the filter. Okay, perfect. And now the reasons of why the LP works are essentially two things, right? And these are the main properties that we are using in our analysis. First, let me call this the approximation guarantee. Okay? So if you look at the expected weight, right, of the solution, right? So I'm sampling according to the LP, right? So then on expectation, I'm getting exactly what the LP gets. It's exactly that. And the expected opt for the LP is, of course, the expected integer out, right? So I'm upper bound in the benchmark. Have an upper bound in the benchmark. And then the second key property, right? This is very important, is what I call the blocking guarantee. The blocking guarantee. And the blocking guarantee is that when you look at every bundle, every possible hyperedge, on expectation, the number of bundles, right, or hyperedges blocking this other hyperedge is at most k, right? So for the AP, this is clear, right? For the AP, this is clear. But the nice thing is that in the LP, on expectation, you can also satisfy, right? And again, because I'm sampling exactly according to the LP solution. So let me quickly show you the calculation. So if you take the expectation of the number of, again, like, blocking means that you intersect the hyperedge, right? So then the expected number of bundles blocking F is just, you take the summation over the agents, you take the summation over the bundles G that intersect F, right? And now you take the value of the LP in that pair, so X, J of G, right? So this is the expected number of bundles blocking F, according to my independent one. Okay, and then this you can write equivalently in the way below, right? So now you take the summation over every item in F, which is the fixed bundle. Then you sum over every agent, and then you look at every hyperedge incident to the item, right? And then if you look at this from here to the right, right? From here to the right, this is exactly the LP constraint, the first LP constraint, right? So the last two summations. These things is exactly what I have in the LP, and this is at most 1. Okay. So then this is at most 1, and you have a 1 per element per item in the bundle, and the size is at most k, so it's almost. See. Good. Okay, perfect. Yeah, but this is great because this is essentially everything that we need. So to get the same guarantee that I showed you before, these two things is what we need. So it's an approximation guarantee and it's the blocking property. Okay. But now, I mean, the good thing is that first I'm using the LP, right? So I can efficiently run my algorithm, right? And then I have to check the blocking guarantee, right? But at least in this case, it's simple, it works. Using the same idea, okay, but of course with some slight variance. we can also give algorithms for other two settings. So one is the prophet secretary setting. What do I mean in the prophet secretary setting? Now every agent has a random valuation again. Right? But now the distribution, now they are not identical anymore, right? So the distribution might depend on the agent. But the agents come in random order. Okay? So it's like a point in between, right? Between the prophet with arbitrary arrival order that Andres showed yesterday, right? And these are the fully IID model, right? In which they are all identical and therefore the order doesn't really matter. So here is random order, random valuation. Okay, and in that setting, again, like using a very similar idea, you can get a 1/k plus 1 approximation, which is exactly the approximation of the result by Andres, right? But for this prophet setting, right? So it's fixed order, a random valuation. But the nice thing is that we can get this approximation, right? Like matching exactly this the approximation factor in the other setting, but only using samples. Okay? So this is the nice thing. So one way of seeing this, or one way in which I like to see it, is that now you can use samples, right? So you need less distributional information, right? But at the cost of looking the agency in random order. Okay? So this is the thing. So you pay random order, but now you need less distributional information. And for secretary, again, using a similar idea, you can get a k to the minus k over k minus 1 approximation. It looks a little weird, the number, but it's essentially 1/k. Yeah, 1/k. Yeah. So then for IID, prophet secretary, and secretary, you get 1/k. And sorry, and secretary is exactly what essentially Anupam just presented, right? Random order, right? But now the evaluation functions are totally arbitrary, right? Excellent. So I will not give the full analysis. It's very similar, yeah. But let me just show you the algorithm that we use for the prophet secretary setting. But I will simplify the exposition a bit. So first, I will show it in the matching setting. It's exactly the same, but I will look at matching. And second, let me consider the single-minded setting. Yeah, what do I mean by single-minded? Is that now every agent puts all the weight into a single edge, right? So now essentially the game is that every time that an agent arrives, right, what you see is that you see the valuation of the agent per a single edge, right? Like edges and agents and edges are linked, right? So adding correspondent. It's a simpler setting. Of course, it's captured by this other more general setting, but the idea will be the same, right? Okay, so how does it work? So these numbers that I have here next to every edge. So these are going to be the sample values. Okay, so I have access to one sample per edge, right? And these are my values. Okay, and then when I actually see the values, right, from the agents, then I will do the following. Let me replace the sample that I have for this edge by the real value, right? So in this case, in my sample, I had a 12, but the real value is a 2. So let me forget about the 12. I will replace it by a 2. And now, with that 2 and the other numbers that I had that didn't change, I will compute the optimal matching, maximum weight matching. Okay. And that tells me, well, you have to select 5 and 7, right? And then you say, well, is this edge in the optimal solution? It's not, right? So then I don't take. I pass. Then I have a new agent arriving, right? In the sample, I had a 2, let me replace it by a 4, okay, the real value. And I do the same game. So let me compute the maximum weighted matching. So now the edge is in the optimal matching. And therefore you want to pick it, right? It's a good choice. You want to take it. But you have to check feasibility first. Here, simple, because I didn't pick anything before, right? So feasibility remains, right? So that's what you take. Good. Right? And then you continue. You continue again. So you replace the 3 by a 5. Compute the optimal matching, didn't belong to, so you pass. Okay? This is the algorithm for profit secretary. Yeah. How much? Yeah. And the analysis is very similar. Yeah. So you have to be careful in the sense that now the sketch that I showed you, you have to do it in a slightly different way. Yeah, but not so different. I mean, the arguments at the end rely in these two properties that I showed you, the approximation guarantee and the blocking property. As long as you have these two, then you can recover an analysis for a different factor, of course, but the analysis will go. Okay, and a few things that I can say about this algorithm is that first, in the IAD setting, it's also sample-based. Right? I only need samples, essentially. I'm sampling every time. But I'm using O of n per agent, n per agent. But in Profit Secretary, I'm using a single sample per agent. Yeah? So this is nice. Again, I put it in contrast with the Profit setting, right? Where you have fixed order, but any random valuation. Here it's a point in between, so then samples are enough, but at the cost of having random ones. And then the secretary algorithm runs in polytime, right? Which is also nice because now we're solving DLP. And actually this answers a question by Tome and Michal in a paper in the C22. Yeah, whether one can essentially match this factor, but efficient. Right? Let me also mention a few things about extensions. Yeah. So before I showed you essentially extensions, but looking at the arrival order. Now let me look at the combinatorial structure of the problem. Yeah. So far, I showed you everything for K match, K bounded set. Okay, but again, for everything to go through, right? Even the sketch that I showed you. The only important thing essentially is the two properties that I showed you, approximation guarantee and the blocking property. And what we can show is that it is possible to formalize this notion. Yeah, how do we formalize it? Well, essentially in the IAD setting, what I did at every time was I solved DLP, right? And I used the solution of DLP to construct a random solution for the problem, right? So this is what I did. I solved DLP, and then I did independent rounding, and then I got a solution for the IAD, right? Maybe not feasible. This is the thing, right? Because since I did it fully independent across agents and hyper edges, it could have blocked, right, in my sampling. But it doesn't matter because I'm only using this information, right, to compute these properties and expectation, right? And then to enter in my solution, I'm still going through the filter, right? So I will not violate feasibility at any level. And therefore, instead of solving an LP, let me say that for the problem you have, there exists some algorithm, some machine that will give you a random solution that will satisfy exactly these two properties that I showed. Approximation guarantee, blocking property. And that machine, we call it a certificate sampler. So the definition is a bit more complicated in order to capture a more general setting, but it's in your mind, I think that you can think that this is essentially DLP. It's DLP, you take the solution and then you use it to construct a probability distribution, right? And using that machinery, well, we can capture several other settings, so including different classes of matrix. So yeah, I think it's a general object in that sense, right? And it's the same idea. The analysis is exactly the same, doesn't change. Yeah. And the other thing is that even, I mean, since I was talking about combinatorial options, naturally every agent has a valuation function, right, over the bundles. But when you look at different classes of combinatorial constraints, for example, if you look at matrix, yeah. So typically in all the models, we consider that agents were associated to an element in the ground set of elements in the matrix, right? For example, if you are looking at, I don't know, let's say a uniform, right? So every time that you have an element arriving, it's an agent. But now with this idea, you can capture also the setting in which now every agent has a valuation function over the elements in the ground set. It's not associated with exactly one element. It has a valuation function over the full set of elements. Right? Like in combinatorial options, but now with different type of constraints. This is the only difference. Yeah? Instead of looking at kin matchings, you may have other type of constraints. And everything goes through. It is really the same. So for example, if the idea that when we solved the LP for kin matching, didn't really make any difference if you had a weight function over all the bundles or you were associated to a single bundle. It's exactly the same. It doesn't change anything. Good. And finally, let me mention a few questions that I identified when writing down the presentation. Yeah. So, well, first, we also provide an upper bound, okay, of overlap K over K. So there is a gap. So the upper bound works even for the IAD setting. It is not a huge gap, but there is some room. What is the answer? I have no idea. To be honest. I mean, I would like it to be 1 over. I don't know. No, I don't really have to say. A second question is, now when you look at the data-driven variant of Prophet, the one that Andres presented yesterday, but now data-driven, so you only have sample. I think in that setting, the 1 over K is, we don't know. That's it's unknown. I think so.
Fixed order.
Fixed order? Yeah, fixed order, random valuation, but now data-driven, I think there is no 1 over K approximation. I think that's an machine. Like essentially replacing all the distribution, the full distribution of information by just in sample and getting 1 over K, and we don't know. And for NAB, I think this is also a question that at least I don't know the answer. So in our approach, we sample the lot, right? So we sample n times per agent.
But the total like n squared.
N squared, exactly. It's like n per agent, so n squared. It's a lot. I have no idea whether you can get 1 over K, but using less than n per agent. And
But do you care about truthfulness or pricing based or any other?
no, not necessarily. Thank you.
Any questions for Victor? Maybe we can have a couple.
I just wanted to make sure I understood the algorithm correctly. So when you're solving, say, the integer and the linear term, that you're not assuming that you tell the program what choices are. You're not being blocked by previous choices in the algorithm when you're solving that integer program.
At every step, no, it's a new LP.
Okay.
Completely independent from the master. Because I'm using fresh samples every time. Yeah. It's a bit different. It's information theoretical. Yeah, I mean, no, I mean, the instance is a bit complicated, right? But at the end, it's really by proposing an instance, you try to compute the expected opt, right? Then yeah, you get the log k over k. Well, something that I didn't mention is that the same instance, yeah, also gives you an upper bound parameterizing the number of agents, right? Which is you could also do. So in terms of k, log k over k, but in terms of the number of agents, it's something like log n over root n. It's a bit different, but it's the same instance.
There are no more questions. Let's thank Victor.
Yeah, again, we'll resume in like 2-3 minutes.